In this lesson, we're going to be talking about composite functions and inverse functions. We'll start off with the composition of functions, or composite functions. Basically, composite means to put things together, and in this example composite function, we're basically saying we have this function h of x. And what h of x is basically taking the function, this function f of x, and substituting that into g of x. Okay, so it has a statement, the domain of h is set to all of the x values such that x is the domain of f and f of x is the domain of g. Basically what all that means is simply that the domain, your domain of f, that's your x, so you plug a number x into your f function, okay, and you get a resulting number, okay. That's your output of f. Well, that number is going to become the input for the function g, and then you'll get another number. So basically, you work this inside out. All right. I think this will make more sense once we work an example. In this example, we have two functions, f of x equals 6x and g of x is equal to 4x plus 5. We want to find the following. We want to find f of g of 2. That's how we say that. 2 is being inputted into function g, which is this, and then whatever that result is going to be input into the f function. So we work it inside out, just like we do with nested parentheses. So we'll start off and we'll work with plugging in 2 into the g. So in other words, we could say that this is just like saying 4 times 2 plus 5. This part, just on the inside, okay? Because g, function g, is 4x plus 5. And then I'll just carry the f over here. Then I would simply work this out on the inside. So I'll just say 4 times 2, which is 8, plus 5, which is 13. Now that I know what that is, I can I see that I have f of 13. And I want to figure out what f of 13 is equal to. So I'm going to input 13 into the f function, which is 6x. Okay? So f of 13 is equal to saying 6 times 13. Okay? So therefore, and I'm just going to go over here real quick, f of 13 is equal to 78. Let me rewrite that. That was messy. F of 13 is equal to 78. So I would box that in, like so. Now let's look at problem or part B. Now in this case, what's different is that we are not substituting a number into x here. We're just going to leave it as x. So this is just like saying f of 4x plus 5. Okay, because that's our input. Our input's always inside the parentheses in function notation. So since f is 6x, and this is our input, and we always put our input into x, I would rewrite this again as f of g of x is equal to 6. Erase that real quick. 6 times 4x plus 5. Okay? So all we do now is we just keep simplifying that. We distribute the 6. So f of g of x is equal to 24x plus 30. Okay? And that's our final expression. Okay? You can even substitute a function into itself. That's allowed. So for instance, here I have g of x, and g of x is being 4x plus 5. So I would just simply say g of, so this is like saying this is equal to g of 4x plus 5. Okay, so therefore g of x is equal to, so we're going to substitute 4x plus 5 into, guess what, 4x plus 5 up there. So it's going to be 4 times, and in parentheses where the x would be, we plug in this whole mess, this 4x plus 5 and then plus 5. And now we would simplify this. So g of x is equal to 16x plus, and I'm just going to say 25. Like so. So anyway, that's how you can deal with composite functions. The next topic we want to talk about is inverse functions. And to understand inverse functions, you need to know what an inverse relation is. An inverse means you're flipping your x and y. That's it. Your y becomes your x and your x becomes your y. So here's my original relation. Okay, take note of the x values here. And in my inverse relation, notice that becomes my y values. And likewise, my y values here become my x values here. So in a table, you just flip it, just like that. That's what inverse means. Okay. Now there are some cool properties that happen with that. So with these blue points here, these are the original ordered pairs. If you were to graph these blue points onto a graph, it would look like this. Now, when you graph the red points, you'll see the red points here. Okay, so I see the blue points here and red points here. Now, these are a reflection of each other. It's a mirror image. So where is the line of reflection? Well, it turns out that the line of reflection is always going to be the linear parent function. Whenever you flip the x and y around, it's always going to reflect over y equals x. It's crazy, I know, but there it is. Okay, and we'll see that happen with other things. Okay, so for instance, let's take a parabola. Okay, the parent function of a parabola, f of x is equals to x squared, right here. Now, if we just flip the f of x and the x, or the y and the x, because f of x and y are interchangeable, and you graph it, it's going to look like this. Okay, you'll have to take my word for this. This is something we'll get into later, but when we graph it, it's going to look like this. And look at that. It's reflected over y equals x. I mean, awesome. And then here we have a cubic function in blue. See, and if I were to do the inverse of that, so you would take the cube root of x, it would look like this. Okay. So any function, when you switch the x or y, you find it, you find its inverse. The inverse is always going to be reflected over y equals x, the linear parent function. Okay? Now, you can tell if the inverse is going to be a function simply by looking at the original function and doing what's known as the horizontal line test. Okay, so we have the vertical line test to see if a function is if a graph is a function, but we have the horizontal line test to see if its inverse is a function. But it makes sense. Like, I mean, we can see that the inverse of this is going to be a function. It passes the horizontal line test, which has the same rules as the vertical line test. It can't cross more than once, and this will only cross once. But this one is not. The inverse is not going to be a function because the horizontal line test shows that it's going to be crossing twice. And we know that because the inverse, which we saw earlier, looks kind of like this. The inverse is not a function because it would fail the vertical line test. But to save ourselves time, instead of having to graph out the inverse and do the vertical line test, we could just do the horizontal line test with the original function. Moving on. So we want to take this function f of x equals 3x minus 2 and determine whether the inverse of f is a function. And then we want to find the inverse. So we can go ahead, we can take a look at, I just graphed it on the calculator. So it looks like this. It's a line, and if we were to draw just a bunch of vertical lines, horizontal lines, do our horizontal line test, I mean, it would clearly pass. It wouldn't cross more than once. So yes, its inverse would be a function. We just look at the graph, horizontal line test, check it, see if it's good. So now we want to find its inverse. So I can rewrite this equation. Recall, I can rewrite this equation as y equals 3x minus 2. Now all I have to do is flip the x and y, because that's the definition of an inverse. Is we flip the x and y. So x equals 3y minus 2. See what I did there? They switched. Now I need to solve for y. We need to make it all proper again. So therefore, I'm just going to add 2 to both sides. So that's going to leave me x plus 2 equals 3y. I divide both sides by 3. And I'm going to flip the equation around. So y is equal to x plus 2 divided by 3. Okay? You could leave it like that, or you could divide 3 into both terms and use it as fractions, because remember there's an invisible 1 in front of the x, so it could be 1/3 x plus 2/3 is acceptable as well. This might be a little bit, this will probably be more preferred. You'll see this form more so on standardized tests, I suspect. Anyway, so that's it. Now let's talk about notation real quick. So we're going to say functions f and g are inverses of each other, provided that if you do the composite of g into f and you work that out, it comes out to x, and that's it. Likewise, if you composite f into g, that should work out to be x. Okay, just x. If that's true for both cases, they are inverses of each other. The function g is denoted as f to the negative 1. That means f inverse. So you can have f of x, or you could have the inverse of f of x. And in this case, we're calling that, that's the same as saying g of x in this situation that they're talking about here. But that's how you denote inverse, to negative 1 exponent. Okay, so let's go ahead and verify that, in fact, f of x and this inverse of f of x are indeed inverses of each other's. Okay, we're going to verify that by compositing one into the other. So let's start off with doing f of inverse of f of x, like so. And so that's going to be like saying f of 1/4 x minus 1/2. So therefore f of inverse of that is equal to, so we're going to substitute this whole thing into the x there. So that's going to become 4 1/4 x plus, minus, where's my eraser? There it is. 1/4 x minus 1/2. So all that went into x, the x up there, plus 2. And so we distribute the 4 here and here. So that's going to be 1x minus 2 plus 2. And then minus 2 plus 2 is equal to just x. So as we can see here, f of inverse of f of x is equal to x, just like it was showing. So that checks out. Okay, check. Good. All right. So let's test it the other way around. Okay. So let me get myself some space here. So now we're going to do the inverse of f of x, which in this case is going to be, this is equal to the inverse of f is equal to 4x plus 2. So we're going to substitute this whole thing into the x here. So that's going to be 1/4 and then 4x plus 2, okay, minus 1/2. So I distribute the 1/4. So that's going to leave me with x plus 1/2 minus 1/2. And plus 1/2 minus 1/2 is equal to, guess what? X. So the inverse of f of x, that's a lot of ofs, is equal to x. So therefore, we have just proved that they are inverses of each other, and if you graph them, they will reflect over the linear parent function y equals x. And dude, I am totally amazed that I did that under 20 minutes. So if that was too fast, pause, rewind, look at it again, and if you have questions, you know where to find me.